My name is Zain Yousaf Fuentes. I'm currently a computer science student. I'm somewhere between sophomore and junior year right now. I'm not exactly sure where I'm at, but yeah, pretty much I'm a CS major, and I recently passed the foundation exam this last semester, and I actually helped somebody on the Knights Hack board. She told me that helped her pass her exam, so she thought I would be a good person to help other people study for their foundation exam. So you might be taking this for the first time, you might be taking it for the second, maybe it's your third time, but I hope that I'll be able to, help you pass the exam this time around or anytime around. So yeah, let's start off. So this session is going to be on dynamic memory allocation, linked lists, stacks, and queues. And yeah, so today's just going to be pretty basic considering it's just the start of the course. So I think this is something that people should have strong fundamentals with. But just in case, we're just going to go over it again in case anyone has any questions. So yeah, so we're going to start off with dynamic memory allocation. So the basics, there's static allocation and there's also dynamic memory allocation. Typically, static would look like, for example, these array initializations we have here, where it's just an integer array. You can either predefine what values are going to be in it. It's going to be to a constant size, or you predefine the size through define a constant, or you just set the value yourself. It's also whenever you use an integer variable, a character variable, even you predefined string is also considered static allocation. But dynamic allocation is going to be when you may not know upfront the amount of data you're going to be using in your program. So for example, let's say I didn't know how much values I wanted to hold and I would take that in from input, then that would be a great time to use dynamic memory allocation. Another thing is if you want to compartmentalize your code and make it like more modular, then you wouldn't be able to return something like a static array declaration or a static like a pointer. You wouldn't be able to return that from a function without using something like dynamic memory allocation. So we're gonna go a little bit more into that and just make sure everyone has the basics. So this would be what static array, like reading in values for a static array would look like. You would just scanf things in. You would, for example, print out the values. Same thing for if you use a defined constant, like on static array 2, it's a predefined size, and they would work the exact same way. So I'm sure we all know static allocation. So let's just go into some more DMA. So ways to DMA. A lot of people tend to confuse the three different ways to DMA, but really it just comes down to three functions. We have malloc, which is where you're going to give the size of whatever type you want to work with. So for example, if you wanted to make an array of integers, you would use size, and your type would be int times n, and you can say n is just whatever variable you want to, whatever integer variable you want it to be sized to. So for example, if you want 5 elements in your array, like an array of 5 elements of type int, you can use something like malloc. And yeah, it'll return a pointer to newly allocated memory. It'll be a pointer of the type. It can fail and it can return null, but we don't have to worry about that. There's some teachers that they will want to test you on that, but for the most part, in the scope of the foundation exam, you're not going to have to worry about that. Then there's calloc. Calloc is another type of function that is used for dynamic memory allocation. And calloc is a little bit different than malloc. A good way I say that you can remember it is, since calloc starts with C, it takes first the count of elements. So C for count, C for calloc. It takes in the count of elements, and then as a second parameter, it takes in the size of whatever type. So for example, if you want to declare something like a frequency array, which typically you initialize it to, you zero out the whole array. Like if you want to count how many C's or A's or B's or Z's there are in a specific word, you would calloc typically an array full of zeros of size 26, since there's 26 letters in the alphabet. So yeah, that's one case you would want to use calc, mainly frequency arrays for the purpose of the foundation exam. And realloc is another one where you're going to want to use that to expand something that you dynamically allocated, like with malloc or calc. So let's say you had 5 elements, an array of 5 elements that you dynamically allocated, but now you need, for whatever reason, 15 integer, like enough space to hold 15 integers, then that's where you use something like realloc to reallocate the size. It'll return a pointer to, it could be at the same location, or it might be at a different pointer. So that's something you have to always be wary about. And it can be used to downsize, free, or expand memory that was dynamically allocated. It's not common, but it can be used. I have personally never seen it on a foundation exam, but it's good to know how it works. Okay, so next slide. These are examples of dynamic memory allocation right here. And I apologize, in the left function, I did not define X. X should be starting off at 0. But for example, if you wanted to declare a frequency array based on a specific string, like for example, we're going to do lowercase word, we're going to initialize an array of size 26, and each element is going to be of size of integer. So we're going to iterate through the string, and with a pointer, we're going to go through the whole word. And for every specific index that a word maps to, so let's say we have letter B. B is going to be the second letter in the alphabet, but since it's an array, B would actually be index 1, and A would be index 0. So it would just go through and index properly based on whatever letter it is, and count up the frequency of the letters in the word. But the whole idea of me showing you this is just so you see when you would use something like calc. And let's say you want to make an array, but you don't care about starting everything off at 0, and you just want to set whatever predefined values, like non-zero values, then you can use malloc in that case in the make array function. But calculate frequency array is going to be a case where you preferably want to use calc. Now you can do the same thing that you do with malloc to simulate, or you can do the same thing that calc does with malloc, where instead of reading in scanf for a specific value, you would just set it to 0. So array of X equal to 0 up to the 26 letters in the alphabet. So that would be one way to do it. But typically you want to split up when you would use calc and then when you would use malloc. And a lot of people, they tend to have issues with DMA, typically reading in things, making sure they efficiently, they don't overuse the memory for something that they need. But really DMA is, in a way, the backbone of a lot of CS1, because we have linked lists, stacks and queues, which is what we're going to cover today, heaps, binary trees, tries, I split heaps twice, hash tables, and even merge sort uses that when you're merging, because you need to have like a specific size to both components that you're going to be merging from. So it's important to be good at dynamic memory allocation. And if I recall correctly, dynamic memory allocation is one of those sections on the foundation exam that has some of the lowest passing rates, depending on the type of question. Sure, there's a lot that are easier, but there's some that are more technical, like those that were on the one that was on the previous foundation exam was a little more detailed. So it's important to know that, because normally it's 10 points on the foundation exam. So if you were to dynamically allocate a struct, I defined here a little bit more complicated of a struct. So we have a struct of a student, and it has a grade, a pointer to a character array, and a pointer to an address struct. And the address struct has a street address, so a pointer to a character array. Then we have a zip code, we have a city, we also have a country code, and these are all strings right here. Street address specifically is going to be malloc, since we haven't predefined the size like we did for city and country code, and same thing with name. But this is what it would look like. So we would need all the information. We can read it in here, but let's just assume we read it in somewhere else, for example, in main, and then we wanted to use this function to return a pointer to a struct that has all this information already filled out for us. So we would have to malloc the student. We would then have to set the grade. And the reason I'm doing grade first is because I kind of want to get out of the way the things that are statically allocated. So we wouldn't have to do a malloc for grade, but we would have to do a malloc for name and address data since they're pointers to, of their own type. So name is a pointer to, a collection of characters, and then address is going to be a pointer to a struct of type address. So right here, we would malloc based on the length of the name that we got, and we would copy it over. Then we would malloc the address struct, which is address data right here. Then we would set what is statically allocated. So zip code is an integer. We already have that there. And then city and country code, those are already predefined sizes, so we don't have to malloc those. So that's why I chose to string copy those two. And then afterwards, we have something that we do have to dynamically allocate, the street address, since we don't have a predefined size right here. So we would have to allocate that. And the way that we know the length of this is we can use string.h, and we can get the size of the street address that was passed into the function. And we have to account for the null terminator, so that's why I did +1. From there, you just copy over the street address that you pass into the function into the location. So that would be in the struct of the student, in the pointer to the address struct. That's where you would copy it into the street address member. And then from there, we're done making the student. So that's a more complicated example of how to malloc and set up a struct that we just malloc and then fill it out. But this one has a struct, it has a pointer to a character, a pointer to another struct that also has pointers inside. So it's good to be able to do the harder cases, and that you can solve the easier cases. This would be 2D dynamic memory allocation. So there's many programs, for example, an algorithm like flood fill. There's also other programs that you might come across doing projects in CS1 where you have to do a 2D array. And this would be one way to initialize that. So we would have an outer array that is just pointer to arrays of characters. So let me just visualize this right here. So we would have something like, this is what we have right now. This would be board, and this is of type character star star. Let's say we define it to size n. Let's say n is 3. So these right here, they're pointers. And as of right now, they're not pointing to anything. But if we go through the next lines, we're going to iterate through each of these pointer to pointers, and then we're going to initialize them to the size m. Let's say for the purpose of this, m is of size 4. So we're going to iterate through this. At the for loop, we're going to be at x equals 0, i.e. I use x's for my iteration. So x is going to be equal to 0. And right here is where we're going to dynamically allocate something of size 4, a character array of size 4. Then we're going to be at the next iteration, x equals 1. This is also going to be malloced. And the same thing when x equals 2, we're going to malloc this. And also note that I initialize the whole board to a underline. So really it would look something like this. This is just initializing the 2D board to, a value that just means that you haven't done anything, for example. But this is what dynamic allocating a 2D array would look like. You have to deal with the pointer, the array of pointers, and then each location in the array of pointers is going to point to a pointer that contains the array that you're going to be holding most of the data in. So this one is just, this array right here is just holding the pointers to the real data that you want to store, which is going to be right in here. So for example, if you wanted to access the location, like this location right here, that would be board of 1, and this would be index 0, 1, 2, 3 of 2, and that would give you access to this right here. Since you dynamically allocated, you're not going to have any seg faults. And from there, you just return the pointer to the 2D array. So that's just a quick example. Freeing memory, it's something that is important when it comes to DMA, because if not, you're going to get points off. You guys probably have gotten points off for not freeing correctly through Valgrind in class. And it's important to free your memory, because if not, then you're going to have memory leaks. And memory leaks typically are not good. And specifically for the foundation exam, if you don't free something, then they're probably going to take a couple points off. And, you know, we want to keep as many points as we can. So it's a way that we can cut down on memory usage if we only use precisely what we need to at any given point. So all you have to do is just call free. So for example, to free this board, we would iterate through every single array in the array of pointers, and then we would free that whole array. And afterwards, we would free the array of pointers. So let me just go back to this example right here. Let's just erase some of this stuff. So again, we would have to iterate through this array right here. And as we iterate through them, we're going to have access to these arrays that they point to. So the reason that we can't just go ahead and say free board is because then if we free this area right here, we're going to lose the links to each of these arrays that they're pointing to. And if we lose those links, then that means all of this data right here has been lost. We have no way to get back to it. And if we have no way to get back to it, then we can't free it. If we can't free it, we have memory leaks. So you have to iterate through the array of pointers. And let's say you're at x equals 0. You would want to free this member. This is what it's pointing to. So we have this right here. So this would be board of 0. And we want to free this. And we want to repeat this process for every pointer in the array of pointers. So we're going to free this one. Then we're at x equals 1. It would also free board 1. And same thing here. When x equals 2, I'm going to be at board of 2. So this would have been freed. This would have been freed. This would have been freed. And after we freed everything inside, then the last thing that we have to free would be this array right here. Because although we freed everything that they point to, the pointer to array of pointers, it takes up space itself. And actually takes up more than, a single integer would. So we would have to free that to fully liberate the board from memory and say, okay, we have no memory leaks at this point because we freed everything in here, we freed everything in here, we freed everything in here, and then the last thing to free was this. And now we have nothing left that is unfreed or that is not freed that we can reach. So that's how you would free a 2D array. As for freeing a struct, if we go back to the student example, one big rule is for everything that you malloc or calloc, you have to have a free. So if we go back to the example of the students, when I allocated the students, we noticed that The student itself, we mallocked. Then the student's name, we had to malloc as well. The student's street address was another thing we had to malloc. And the reason we had to malloc that, oh, and also the address struct itself, we had to malloc. So these are pointers, and we're not really provided the pointers in here anyway. So we would have to, since we malloc them ourselves, we would have to free those. So when it comes to freeing the struct, when it comes to freeing the struct, we would have to free everything inside that was malloc inside of the struct before we free the struct itself, because it comes down to the same reason as this 2D array. Let me just get this strong. So in the same example of the 2D array, we would have these boxes. Even though we're doing struct, the same logic applies. You cannot free this right here before you free what is at each member of the array. Because if you end up freeing this array of pointers here, you lose access to all of this memory. And if you lose access to all that memory, you can't free it. And if you can't free it, you have a memory leak. So same thing with the struct. So let's see what our struct had. Our struct had, let's say this is our student right here. So our student. And then, we had a couple things. We had age. Sorry, it was the grade. He had a grade. He had a name. This name pointed off to something else. So this is a character array. And then he also had a address data, which pointed off to another struct. And this struct had a couple things. So this one had a street address. Let me draw this a little smaller because it's going to get a little big. The struct had a street address. Struct also had, in terms of things that were dynamically allocated, that was the only thing that was dynamically allocated in the struct. But another thing that we had was the zip code. But this one is a little different. I'm not going to draw it the same way that I did the street address, because I want to show that these are pointers. Even though it would look the same, zip code was an integer. Even though the city and country code, that's what I meant. The city and country code, they would look similar since they're also character array. So you have country code. We don't actually have to free those. So this one was to size 4, and this one was to size 50. So let's think about it. What have we mallocked? I'm going to write in red what we've mallocked. We've mallocked this right here. We've mallocked the name, but the name is really pointing to this right here. And we also mallocked the address data. The address data points to this whole struct right here. Inside of the address data, which we mallocked, we also mallocked the street address, which is pointing to this right here. So in total, we have 4 things to malloc, but like the same reason for the 2D array, if we free this struct right here, we're going to lose access to all of this memory here. And we don't want to do that, because if not, then again, we get a memory leak. So you would want to free everything in the struct first. And it doesn't really matter which order you do it in, but you kind of want to go, like if you have something that's a nested struct that's a pointer to and it has a pointer inside of it and so on, you can start, for example, at the top level. So the first thing in the student array, in the student struct, we have the name. So we can choose, okay, let's call free on this name. So we free this. Now this memory is freed. We're not using it right now. It's not allocated to us right now. Then we have the address data. We can go into address data, go to the street address, and we see that the street address, it was a pointer, so we can free this out because we mallocked it. And now we're good. Now there's nothing else in this address struct that, was malloc. So if we end up freeing this right now, this whole array or this whole struct, then at this point, we're done. We have no memory that should be freed, but hasn't been freed at this point. So we would be good to go from right here. So right now we freed the name and the student struct. We've gone into the address data. We freed the street address that was in the address data. And now we just freed the address data itself, the address data struct. So now at this point, we're only left with the name, the address data. The address data was freed, the name was freed, and grade is just a static variable. So we don't have to free that. So at this point, we're completely done with everything that depends on the student struct. And now that we're done with everything that depends on the student struct, we can free the student itself. And then now at this point, everything related to the student has been freed. But I just want to I just want to say that you cannot free the student before you free what the student is composed of, if that makes sense. So yeah, that's how you would free a struct. It has like a couple levels of nested structs and pointers and so on. So yeah, this is pretty much the same example. This would be if you wanted to free a 1D array of structs, you would have the iteration, you would go through all n students, free the name, free the street address, free the address data, since those were the things that were malloc. And then you also ended up mallocing the array itself, so then you can free the students. Now, as for 2D array, it will be similar to the 2D array example that I gave. So you have a 2D array of students. So imagine we had this same structure, but this was in a 2D array. So we had something along the lines of this. And then inside of every little box, we had this entire structure. Then in this case, you would have to, iterate through the rows, iterate through the columns, and at every column, you would have to do the same process. Free the name, free what's inside of the address data, free the address data, then free the student. So it works similarly. So you would still free the student row, and then from there you can free you'd free the student row, and then you would free the pointers to the array of students. So it'll work pretty similarly. So I know that was like a long time to spend on dynamic memory allocation, but now we're going to move on to linked lists. Does anyone have any questions? I know I haven't checked if anyone has any questions, but let me check. Okay, so that makes sense. Is free not a function of DMA? Why is in star in parentheses in the malloc array? So parentheses in the malloc array. Let me go back to the example. Can you, if you don't mind, can you tell me when that was? Because I just saw it right now. Star in the array of, I think it had to have been here. Star in the parentheses of the malloc array. Okay, I don't see an instar here, but if you mean this right here, where it says malloc size of int star n, I don't mean that it's a pointer to an integer. I mean that I'm just multiplying that. So if I have an n, let's say n is 10, and I want to have 10 integers, I would do 10 times whatever the size of an integer is, and then that'll give me enough space in memory for 10 integers that's dynamically allocated. You were talking about free as well, so yeah, that was like the only part that I had allocated an integer array. So if you could just specify, and then I can go back. I think they may have been confused how you wrote them out. Like, okay. All right, so we're gonna move on to linked lists. So linked lists typically used when you don't know if you're gonna have enough space for whatever it is that you're gonna be representing in the linked list. So I know that's kind of vague, but let's say you want to create a collection of items, let's say integers, that's 1 million elements, but you might not have in memory continuously 1,000 blocks like for integers, right? So you might not have space for 1 million integers right next to each other all in one block, but it might be scattered out through your computer. So for example, if we have, let's say this is memory right here. This is your computer, and this is address 001, 002, 003, 004, and so on. You know, you might have space for, let's say, 3 elements right here. Let's say this is an array of size 3. You might have space for this, but there might be a case where you have something occupying. Let me draw this in a different color. There might be a case where you have something occupying this space, or really, you know, a considerable amount of space after that. And you might not have space for 3 integers, for example. Now, this is pretty bad example because like normally 3 integers, like your computer can find that. But imagine you want to do, you know, 1 million elements. Then that's when your computer might not be able to find that because it might be blocked off by something else that's using in a continuous block of memory. You know, it'll just interfere. It just won't be able to find it all in one space. But that's where the idea of linked list comes in. So a linked list will say, the real purpose of it is, let's say you want to allocate something right here. You want to have an integer in this location in memory, 001 and 001, and you want to add another element. It'll go here, but let's say in memory you have this block right here completely occupied by something else in your computer. Then it doesn't necessarily have to go right here or right here. It could jump somewhere else in memory. It could jump here and say, okay, I found one block, so the space for one node in here, or it can do it somewhere else, for example, in this address right here and say, okay, I found it right here. So we can link up to this because I found space here. So there's a clear advantage where you might not have space for, you know, something gigantic because it might be taken by something else in address like 004, 005, but you might be able to find it scattered or like jumping through the memory like 001, 003, 007. And then that way you could have a collection of, for example, 1 million elements, and it doesn't have to be all, you know, in one huge block. So that's like why you would use a linked list. The basic structure for the most part, it's struct node, and then you have int data and struct node star next. So that star is just a pointer. And I remember the first time I saw this struct node with a struct node inside, it's kind of weird to look at, but it's pretty much just pointing to another. It has a potential to point to something of its own type. So just like in the same example, let's say things shaded in black are linked lists. So we can point to something else that's also a linked list from a linked list itself. So this right here is really what the next pointer is pointing to. From here, the next pointer of 003 would be pointing, for example, to the address here at 007 and so on. So that's all it's doing. So let's talk about one case. We're going to talk about insertion at the head. So insertion at the head, when it comes to linked lists, typically is used. You can use it on a regular linked list, but typically it comes up when you're dealing with stacks. So let's think about how something like a stack works. Let's say you have a stack of plates, right? So this is your stack of plates. Or a better example would be a stack of papers. So let's say this is one paper, this is another paper, another paper. Let's say this is your teacher grading your test. So your teacher, normally he's probably not going to choose something in the middle. He's probably going to choose what's at the top of the stack. So pretty much what the linked list representation of adding on the head would be is we have something like this. And let's say I want to add another thing on top of the stack. And if we're connected in such a way, like this node 1 points to 2, and then 2, the node with 2 points to 3, then we would want to link this one to point to the old top. And now pretty much what it looks like is, let me go backwards. Now this one points in such a way that it's at the top. And really, when it comes to inserting on the head, this would have been the old head, but then now that you just inserted onto the top, then this would become your new head, like for the purpose of the linked list. So now you wouldn't access the linked list right here, since now it's not the head. It's the head that was previously there, but then now that you added something on top, then this new element assumes the top of the linked list. So the code for something like that would look like this. So we make the new node. And first of all, the SSL node is going to be like the same type of struct that I defined here. It's just a different name for it. Instead of node, this is for like singly linked lists, which is typically what we're dealing with. So I called it SSL node. And we're passed in the data. So new node, it's gonna store a pointer to a malloc node, and we have a make node function that's gonna take in data and make a new node. So for this example, if we go back to it, we're gonna make a new node. Let's say we want to make a node with a 7 inside of it. So we just made this somewhere random in the memory. Notice how it's not all in a nice neat stack. It's just made somewhere randomly in memory. And we want to add to something that is already our linked list right here. So if we follow what the code was, let's just have it set up right here. So if we follow the code, we made this new node right here at line 1. Then if head is null, then we just want to return this new node. So let's imagine that we did not have this right here. We didn't have anything at the linked list. I'm going to use X to denote null. So for the purposes, like, you watch me doing this, I like to use X as an example for null. So let's say we have a linked list. Instead of having all this stuff right here, we're just null. We have nothing. Like, it's just completely empty. So in this case, if we're inserting at the head and we don't have a node, we don't have to connect it to anything else in the linked list. And since we don't have to connect it to anything else in the linked list, then we can say that this value is going to be our new head in the linked list. So we would just, instead of rerouting anything, because there might be the rest of the linked list, we don't have to do that. So this value is now going to be our head, and our linked list would not be null anymore. So 7 is pretty much going to be our linked list. And also in the make node function, this would be pointing to this right here. So it would be pointing to null when we make a new node. That's just like a definition that I made up. Every time that you malloc, it's going to initialize next to null. So let's say we want to insert onto the same linked list that has 7. Make a different color. Let's say I want to insert a node with 8. We're going to have 8. So we just malloced it. It's not connected at all to the linked list. From here, we're going to we're going to see, okay, our head is not null. So we're not going to return this node to be our new node. We're not, this is going to be our new node, but we're not going to return it to be our new head. We're going to see, okay, so head is not null, so we're not going to return at that if statement, but new node's next is going to be equal to the head. So the current head would have been 7. So we're going to say, okay, this is going to be pointing now. The next of this is going to be pointing to the old head. So our old head was 7. We just rerouted the new node, which is going to be our new head. We routed it to the old head. And by rerouting that to the old head, now we have access to the whole rest of the linked list. Now, this doesn't really look like much, but let's say you had, in this example right here, let's say we had a bunch of elements like this. And then this was null. So we had 1, 2, 3, 4, 5, 6 elements in our linked list. If we were to, not link it up and we just return this node right here, we would just lose track of the rest of the linked list, which is this area right here. So pretty much it would make the new node and reroute it to right here. And then we would return this to be the new head. So in main, it would be something like we would have a SSL node. This is in our main right here. You could start off at null. Then we would be assigning list every time we call insert front, because we don't know if it's going to, change, or it's going to change the head every time, but there's certain functions that only sometimes it'll change the main head of the list, and other times it won't. But in this case, since we're adding to the front, our head is always constantly changing. So we have to update the pointer to every single time. So we would pass in list. And for an example, let's do 7. Let's insert another element. So insert front of list 8. Let's do another element. To 9. So at the start, we have nothing. We just have an X. That means no. Now we're going to reassign list to be equal to insert front of list 7. We're going to pass in 7. So we're going to make a new node. Oh, wait, I moved it over. Okay. So our head would have been null. We had made a new node. So we're just going to return the new node. So now list, instead of pointing to null, it's now pointing to this node right here. Now we're going to go on to the next line. List of insert front list 8. So we're going to go into the same function. New node equals make node of data. So we're going to make a new node. It's going to be 8. And now we're going to see that it's not null. Head is not null. It's equal to the pointer of 7 of node 7. And then we're going to set the next of this new node that we just made, 8, to point to the current head. The current head was just 7, right? And then we're going to return new node. New node in this call was 8. So now our list, instead of pointing to 7, it's going to be looking like this. So list is going to be pointing to 8, that points to 7, and this points to null. And now we're going to do the next line. I'm sure you guys get the idea, but I'll just go through it. Going to make a new node, 9. We're going to see head is not null. So we're going to reroute the new node that we just made, which is the node containing 9. Point it to the head, the current head that we passed in. And I'm going to return new node. New node is 7. So that means list is going to be, new node is 9, the node containing 9. That means list is now going to equal, it's going to point to the node containing 9, meaning that our new linked list is going to look like this right here. So we inserted front, we started with 7, then we go 8, then we go 9, and this is our final linked list. So does anyone have any questions so far? So I know this is off topic, but at some point will you cover pointer arithmetic? Yeah, I can do that. I can do that for sure. We can do that. I guess I can do that at the end because it's more niche. It's not really something that that comes up often because typically they like to see you doing, they like to see, let's say you have an int array. Let's say this is like size 5, and you want to do a for loop. This is going to look weird for a lot of people, but this is actually something you can do. So let's say we can call this X array, and then let's move this over. I'll just write it now, but I'm not going to go over it, but I'll just introduce the example. Let's say we know it's of size n. This would be a way that you could print an element using pointer, or print a whole array of integers using pointer math or pointer arithmetic. So yeah, this looks really weird. I can explain it later. I'll do that later. But yeah, that's insertion at the front. Now we can do insertion at the tail. So, and I'm just not gonna show the code right now. I know I kind of flashed it, but let's say we want to insert at the tail. There's 2 ways we can do this. We can insert at the tail. That can be done iterative or it can be done recursive. But let's start with the iterative version. So the function is going to look something like, let me just call it node actually, make it simpler. Okay. So one thing we would have to do, regardless of if the list is null or it's not null, is we're going to want to make a node. So how about we do that first? Because regardless if we have a null array, or sorry, not a null array, a null pointer to the head, or we have, a list of 1 or more elements, we would still be making a node either to link it here, or we just make it the new node itself. So let's make the node at the very top. So that would look something like node star new node equals malloc, and then we're going to define the size of, it's going to be of size node. Now let's just initialize everything. So it would be new node data. It's going to be equal to the data that we passed in. We're going to have new node next is equal to, really, you don't have to define this right now, but it can be done here. Let's just do it like this. And there's going to be a case where this is going to change. It could change, but let's just leave it like that. Actually, no, for inserting a tail, it'll always be null, but okay, so we made the node. So regardless of the 2 cases, like we have something in the linked list or we don't, the node is always going to be made. So let's say we have any value, it can be 3. Let's say we have a 3. let's say this was a 7. We'd want to go to the end of the linked list. Let's deal with a case where it's not empty first. So we want to go to the end of the linked list. So a lot of times when we're doing things with linked lists, we're going to want to stop. We might not want to stop at the end, but in this case, we always want to stop at the end. But we have to be able to attach it to the rest of the linked list, if that makes sense. So let's say we want to iterate through the linked list and we want to get to the end. So we start here and then we have a pointer pointing to 7. Let's say we move that pointer forward and now the pointer is null. What's going to end up happening is that now if your pointer, let's say the pointer is just PTR, pointer is going to be equal to null. And if pointer is equal to null, that means we don't have access to this next pointer from 7. So we pretty much lose track of 7. And by losing track of 7, we lose track to actually change what the end of the linked list is actually going to look like when it comes to inserting. Because if we were to do, for example, pointer equals, new node at this point, if the pointer is null, meaning pointer's right here, then that's actually not going to change anything because you're just reassigning null. And if you can't really reassign null in that way. So it's just going to point to that, but it's not going to actually change the structure of the linked list. And you're actually not going to be able to access the new node you just made, this node right here, 3. So stopping when your pointer is null is not a good way, to go about this. So let's deal with the easier case first, is if it's just null. So this right here. If it's just null, we technically have nothing to iterate through. So what we could do is we can just return if head equals null, return new node. So that's the same case that I said. If it's null, there's nothing to go through. So the list is just going to assume, whatever the data was. So you already initialized everything. So now this is what your list would look like at this point. If you insert at tail when it was empty. Now let's say you want to insert something into this at the tail. Let's say you want to insert a 9. So you have 7 and this. So right now what we have malloc a 9. We just malloc the 9, it's not connected. But we're gonna want to stop at the node that its next is null. Because that means we're gonna be able to have direct access to the node before the end of the linked list. And by having access to the node before the end of the linked list, which is denoted by null, then we can actually change how the structure of the linked list is actually going to look. So we can set up a temporary pointer that's going to slide through the linked list. So you guys remember, I did an example where we would start right here, then we would end up moving over and our pointer would actually be here and so on. But if we were to have a bigger linked list, it would look something more like this. So we would have a pointer start here. We're not at the end. Have a pointer, move it over by 1. We're still not at the end because the next element is non-null. So now we're going to be here. And at this point, we're at the end of the linked list because the next element, the current element's next is null. So this is going to be our stopping condition because we already ruled out the case where the current node is null, meaning our head is null. So now we're going to iterate through the linked list. And there's 2 ways of going about this. Some people like doing, a temp pointer. So a temp, this can be called current equals head. And some people like moving the head itself since you're only moving it once. Me personally, I don't think that's a good strategy because what if you want to use your head again? Let's say you want to iterate through the linked list in whatever given problem you have. So you want to move through a linked list. So you're going to be here, then you're going to go here, then you're going to go here. But if you keep reassigning head, so now head used to point to this right here. But then now we're going to say head is now here. Then we're going to say head is now here. But let's say I want to go through the linked list another time. Since I used this head pointer that they gave me, then I pretty much lost the head of the linked list by moving the head, if that makes sense. So what I like to do is to have a temporary pointer that I can slide through the array without it affecting, the original head. Because if I lose the head, then I pretty much lose everything if I have to do something later on, especially since this is iterative. Since this is iterative, if I move head, once I move it, it's gone. Of course, unless I save it or whatever, but it's better to just leave it unaffected and have another temporary pointer to slide through the linked list. That way you don't lose track of head in case you have to use it again. So head is pointing to this node right here. So we also have current pointing to that node there. And like we said, the stopping condition would be when the next of where I'm currently at is null. So that would look like current next equals null. And just something basic about, for loops and while loops. For you to even be inside of this part right here, this precondition has to be true. So for you to be inside the while loop, that has to be true, which means that it's, I guess you can say, legal for us to do something like this. Current equals current next. We're safe to go ahead and arrow into this right here because we know that one, current is not going to be null at the start. We already covered that with this if. So that means that we're safe to say current is never going to be null if we have this precondition. It's always going to be non-null, and we're going to stop when the next element is going to be non-null. So we don't, overshoot and move past the last element in the linked list. So yeah, that's one thing that, it's simple and it's very basic, but sometimes people, look over. For us to be in here, this condition has to be true. And that means that, we're safe to access into it. So now at this point, after this while loop is done, we're guaranteed pretty much that we're going to be at the end of the linked list. So for example, linked list like this, 3, 4, 5. So current is going to start what head is pointing to. So head was pointing here, so current is also going to start here. So now we're going to be here, we're going to see and check, is current next null? So is this right here, is this null? It's not. So we're going to move current right here. Now right here, we're going to see the same thing. We're going to answer ourselves the same question. Is current next null? So is this null? It's not null. So we're going to move over by 1. Now here, we're going to ask ourselves the same question. Is this null? So it's null. So that means we reached the end of the linked list. And now at this point, all we have to do is do current next equals new node. And then let's just like analyze what happened here. So we ended up with current right here. Let's say we wanted to insert a new node. Let me do this in a different color. So you want to insert a new node 6. Then we stopped it right here. We stop current right there. Now we're going to set current next to point to the new node that we had made earlier. And if we think about it, we don't really, since we're inserting at the tail, we already initialized this right here to be equal to null. So this is actually pointing to null. And in memory or in C, null is always the same place, like regardless of, where you call it or whatever. So we don't even have to reassign new nodes next, like this node right here is next, because we already predefined it. And it's always pointing to null. So, at this point, we're done. From here, all we have to do is just return head. So that is how inserting at the tail would work out. So let me just erase this right here. and then we would just return head. Let me see if anyone else has any questions. Wouldn't that be current next is not equal no? Oh yeah, sorry, my bad. Yeah, made an error. There you go. Well, current next is not equal no. Oh gosh. Here we go, node. Yeah, I had a couple errors, my bad guys. So it would be of type node equals head. So we start off pointing it to the head, while current next is not equal null. Current equals current.next. We're just going to slide through it. And then after this while loop, we're guaranteed to be at the last node before the null. So we can just assign the current next to be equal to new node. And then from there, we return the head. We know that at this point, we've added the node or the data value to a node at the end of the linked list, and it's properly connected. So, we've properly inserted at the tail. So this is like the iterative approach. So if anyone has any questions, let me know. And this is a problem that I came up with, I think like a day or two ago. So I want to see if anyone can give me any pointers on how to do this problem. So pretty much we have a singly linked list with positive integers from 1 to 10,000 inclusive. And you want to return the minimum value of the greatest frequency. So this one is going into recursion, it's going into linked list, and it's going into frequency array. So it's like, it's a kind of hard problem, but I want to see if anyone can do it. So I know we've done like some pretty basic stuff, but this should be a good change of pace. So for example, if the linked list is empty, return -1, create a recursive solution. So for example, if we have a linked list, like 8 points to 1 and so on, the answer in this case would be 1, and I'll just explain why. So the frequency of 8, it appears 1 time. 1 appears 2 times. So we can see 1 appears once right here, here. 3 appears 2 times right here and right here. 4 appears 2 times right here and right here. And 6 appears 2 times right here and right here. And also, 8 appears once there. So those are the frequencies right there. And we can notice that the most frequent values are 1, 3, 4, and 6. And the reason that is because 8 appears 1 time, but the maximum appearance, like the maximum frequency throughout the whole frequency array, is 2. And there's 4 elements that have a frequency of 2. So we have 1, 3, 4, 6. And the whole idea is out of the most frequent elements, we want to return the minimum out of all of them. So our struct would look like this right here. So it's just a regular linked list node. We have int data, and we have struct node next. And this is going to be the function prototype right here. Function signature. So we have int min of max frequency, node star, head, and then we have an empty frequency array. So we can assume, this is given, that the frequency array is like non-null pretty much, and that it's initialized all to a bunch of zeros. So it's just going to be like a regular frequency array that you probably dealt with throughout CS1. So if anyone has any questions, because I know this one is a little hard to understand, feel free to let me know. So it says, make something that can hold the amount of time the value appear, make sure there's no duplicates. Well, the thing is, you could have duplicates. So right here, like duplicate values, you have 1s, 2 1s, 3, there are 2 3s, 4, 2 4s, and 2 6s, and 1 8. But you want to return out of the most frequent values, you want to return the smallest out of all of them. So let me just do another example. So maybe, if you're not understanding the problem, then it should make sense. So let's say we have a sequence of in the linked list 3, 4, 2, 1, 3, 6, 7, 7, 7, 2, 2. Okay. So this one is kind of long example, but it's good to see it. Yeah, this would just be the next pointer. So I'm sure you guys understand like the way I represented it and all that. So let's do a little frequency array for this real quick. So 0, 1, 2, 3, 4, 5, 6, 7. So index 0, 1, 2, 3, 4, 5, 6, and 7. And in the example that I gave, you're gonna have up to 10,000, but for this example, we don't need that right now. But it'll still be there. So we only have positive integers, so we don't really have to think about 0, but it'll be initialized to 0 regardless. So we have 1, 3. So we would increment this to 1. We go to 4, increment this to 1. We can go to 2, increment this to 1. We would see 1, increment this to 1. So right now for all these we've only seen them once up until this point. At 3, we're gonna see that it's already seen, so we're just gonna increment by 1. Same thing. 6 we haven't seen before, increment by 1. We're gonna see 7, increment by 1, 7, increment by 1, 7, increment by 1, 2, increment by 1, and 3. And 2, increment again, and now we're gonna be at 3. So let's just make sure we did this right. We never saw a 0. That's pretty good because you're not supposed to have any. It's all positive. So we only saw 1 time. We saw 2 3 times, and we saw it right here and right here. So that's 3 times. And then we saw 3 2 times. We saw 4 1 time. We saw 6 1 time, and then we saw 7 3 times. So our frequency array looks good. But the whole idea of this problem is we're trying to see which one are the most frequent. So out of these, which one are the most frequent? The most frequent would be 7 and 2, right? So 2 and 7 are the most frequent. And now the whole idea is out of this pool of most frequent values, you want to return the minimum of them. So the smaller out of all of them, and this could really be like, let's say our array was just, or our linked list was just this right here, 3, 4, 2, 1. They would all have, like, let's say we cut this off right here. Let's cut this all off. So we only have a linked list with 3, 4, 2, 1. Then that would mean we see 3 once, we see 4 once, we see 2 once, and we see 1 once. So the most frequent values are still the same thing, 1, 2, 3, 4. Or let's just think of it in the same way that it came in the linked list, 3, 4, 2, 1. But what's the smallest of these? It would just be 1, because 3 was seen once, 4 was seen once, 2 was seen once, 1 was seen once. But the minimum out of the maximums is 1. So that's the whole idea behind the problem. And if you guys didn't get the function, that's what it looks like. If anyone wants to write it out and try it. But definitely tell me any ideas that you guys have. So it's just gonna be min of max frequency. You take in a head pointer and then a frequency array. So I know this is off topic, but would we be able to go over previous exam in upcoming sessions? Yeah, sure. So 7 and 2. Yeah, it has to be recursive. Yeah, I'll definitely go over previous exams as well. I feel like regardless though, this one is still a good enough problem that it's up there in difficulty with, and it's on par. It's nothing too to insane, but it's hard enough that it might be seen. It might not be seen on a foundation, but it's similar to something that you could see on the foundation because it implements like multiple things like frequency array, recursion, linked list. So, regardless of it not being foundation exam question, it's still a good question nonetheless to understand, because though a solution pretty much banks on how well you understand recursion and frequency array and so on. So, and it's represented in a linked list. So yeah, I'll just wait another 2-3 oh shoot another 2 or 3 minutes before we go into the solution for that. So in the meantime, I'm just gonna write let's see what it says. Has to be recursive. Yeah, still has to be recursive. Let me set up the problem here. Okay, so does anyone have any ideas? When we get to the recursive call, would we say max frequency? No. So the whole idea of this problem is you're going to be recursing once, and I'll just say the runtime up front should be O of n. But yeah, you would have a recursive call that would say, you would go to head next. And yeah, you could use a 10 pointer, but it doesn't really matter because the whole thing with linked list is like each call will have its own state, and in the case of a linked list, the state would be, for example, we have a linked list like this. We're at node 3, a node that has 3, then we have a node that has 2, node that has 1. The state, you can call it, is the first call, the state is this node right here. So the node right here. Then the state in the next call, when you get to 2, is going to be this node right here. The state in the third call will be this node right here. And, if you end up going to null, then the state would be the call right here. So regardless of you having a 10 pointer or not, you having a 10 pointer to pass in like this node right here into the function for this recursive call right here, it doesn't change anything. Like you could pass in a 10 pointer to head next, you could not. It doesn't really matter. It's just at that point, since it's the same thing, it's just whatever you feel more comfortable with. But I will go through it now. Let's see. Does anyone else have anything else to say? Yeah, the index is the same number as you will be. Exactly. So how do you keep track of the frequency counting? So you keep track of the frequency counting. If you think about how arrays and array indexing works, if you just think about what an array is when it comes to a function call, this in reality, it can still be written as something like this. It's still a pointer to something. So it's something fixed in memory that you're constantly looking at. So if you think about it, as you recurse through a linked list, the only thing that is changing is whatever node you're at. But the frequency array itself stays constant. Like it's always just going to be pointing to the same, 10,000 elements right here, But you frequency counting, like let's say you have a linked list and you go through it, the frequency count that you get, in this region right here, it's still going to be the same as when you get here, but here you might increment something that you might have not seen before, you have seen before. So the frequency array, either way, is gonna be the same. It's not changing at all. So the frequency counting, that can be handled. You can like look at the different cases you have with an if check. But yeah, the whole idea is that through the recursion, your frequency array table, it's gonna change, and then there's gonna be a certain point where you wouldn't want to change it anymore. And I'll explain that in the problem. So the index is the same as the number you were working with, yes. What about a statement that checks if there's any index that has a higher frequency thus far, then you are on the currently hard when you make a recursive call? I'm just saying the first thing that comes to mind. So you're definitely on the right track, but I don't think you would want to think about that before you make the recursive call. So let me explain why that might be. So what you're saying is, let's say we have this case right here. You're saying we want to check the frequency of this right here before we make a recursive call. The thing is, you're assuming that the frequency array starts off at 0. It's zeroed out, right? So we have a bunch of elements, right? But the only ones we care about are up to 3. So 0, 1, 2, and 3. So we only really care about this region for this problem, but you would have the whole area. So right here, since it starts off at 0, you haven't really accounted for anything yet. So you can't really just say that, I'm going to invalidate it. I'm going to invalidate, okay, I'm not going to go to this one because I don't see, a reason to go based on what I have right now, because you haven't seen the full picture. The whole idea is you get the full picture from the entire linked list, and then after you've calculated and saying, okay, I've seen 2 times, I've seen 3 1 time, then after you have all that information, that's when you're gonna, do your checks and then return which one might be the minimum and compare against maximum and so on. But if you're going in blindly, like just from right here, since you haven't built your frequency array, we'll just start at 0. If it starts at 0, you have nothing to go off. How would you know that 2 appears more than 3 if you haven't seen the whole thing? You have to see the full picture. So for example, linked list of 1 2 1, then the frequency of the array would be 1 1 2. No, the frequency of that would look something like this. It would look like, let me just write this right here. So if you had 1 2 1, so this is index 0, this is index 1, and this is index 2. So it's not a size based on the size of the linked list, the size of the frequency array. It's just the values that are in the linked list are up to 10,000. So it's going to be from 0 to 10,000 inclusive, all the values in the linked list. So the maximum you'll ever see in the linked list will just be 10,000. But I'm gonna go through the explanation. Do we reiterate over the frequency array again? No. You would do this, yeah, it's based on the value, not the index. But if you think about it, for a frequency array, our value is the index, which is what someone else said. I think that was Nico. But let's go through the explanation real quick. So like I was telling someone else, you want to go through the full linked list before you can make your decisions at every step. So we have 1 2 2 3. Our frequency array would look something like 1, then 2, and then 1. Index 0 1 2 3. So this is what our frequency array would look like. But the only way we can have all this data is if we've gone through the whole linked list. Because someone else asked this. At this point, you wouldn't know, like when you're at this node, you wouldn't know how many 2s there are, how many 1s there are. At this point, you wouldn't know how many 2s and 1s there are. At this point, you wouldn't know how many 2s and 1s there are, or if there's another value. But the only point that you do know everything, you've seen the full picture, is at this point right here, when you're at this node. Because at this point, you know that you're at the end of the linked list. And if you're at the end of the linked list, there's nothing else to consider except this value itself. So if we remember what the base case was, if the list was empty, we're going to return -1. And the reason I did -1 is just because you're going to know right off the bat that the list was empty, because we're dealing with all positive integers. So yeah, you're going to want to go through the full linked list before you can make your decision. So for those familiar with like binary trees, it's kind of like when you do post order, you want to traverse deep all the way until the end, like all the way until your leaves. But in this case, the linked list, you want to iterate, you want to recurse all the way down right until the end. And from there is when you want to come back up once you have, you know, your sub solutions. So in code, we would have the base case if head equals null. This is going to be one case where the list is empty. And you're going to want to return -1. So that's our base case when the list is empty. Now, we're going to want to account for every element in the linked list. But like I said, since the null is going to be returning -1, if we're going to be returning, you know, values like a maximum or the minimums of, you know, all these values based on frequencies and so on, we don't want to have a -1 like passed back to us at any point. So then we don't end up doing, you know, frequency. And I'm just writing this shortly. Frequency of -1, because, you know, we would segfault in that case. So we do frequency of -1, we're going to segfault because, you know, C doesn't allow that. There's some languages that do, but C doesn't, I'm pretty sure. So we're going to handle another case. If head next is null, similarly to like tail insertion, that's when we know we're at the end of the linked list. So we fully considered everything. So at this point, we fully accounted for the frequencies. We would want to return the value of where we are right now. So the way this looks is we have, you know, we would return 3 back to the call where we called 3 from, which would be the node containing 2. But there's something missing here. We haven't accounted for head data. Like we haven't accounted for this element right here. So let's say if we iterate through this linked list, and I know I haven't written the recursion yet, but let's just say I did. If we get to the end of the linked list, the last node, and we just straight up return head data, then we wouldn't have considered the frequency. So this would actually be set to 0, right? So this would be set to 0. And in this case, 1 would be the answer regardless, even if it was 1 as well. But there can be a case where by us not considering the last element, we would, you know, throw off what our actual answer should be. So one thing we're going to want to do before we end up doing this return, like on the base case, when we hit the very end of the linked list, is we're going to want to do frequency of head data plus plus. So what this is going to do is going to account for the current element. So let's go back to the linked list that I had here, and let's restart this frequency array. Zero, 1, 2, 3. So if we follow the code, we're going to check is head null. Head is not null. Head is not null. We're going to increment the frequency of 1. So it's going to be 1. And head next is not null. So this element's next is non-null. So we know that we're not going to return head data, which would be 1 at this point. So at this point, we want to keep going through the end of the linked list because we haven't hit the end. And also we haven't accounted for the end. So right here, I'm going to call this, let's call this sub result. It's going to go to head next. That's the iteration step in a way, like we're recursing to the next element, next element, next element, and so on. And we also have frequencies. And let me see real quick if anyone has any questions. This be a base case, head equals null. Okay, let's see up here. So I see the index, the frequency value is based on value understood. This be a base case. No, it wouldn't be a base case because the frequency, if you mean frequency, like frequencies, then that's a pointer to an array. And that's not what we can return. The function return type was int. So another way, oh, what just happened? Okay. Sort the array. Now we're not sorting this. If head data is equal to data, then frequency of data. The only thing is, what is data though? Like that's the only thing. You didn't really tell me what data is equal to since we didn't pass it in. Okay, so if we use Nico's base case, then we go through the entire list, then recursive call. What does that if statement mean for fitting the function? Yeah, that's also what I don't get because data is not given. Head data is always given, but if we encounter a different number, we increase, it's counting the frequency array, but I feel like we don't need it. No, it's unnecessary because regardless of if you see it or not, it'll just increment it. Yeah, Timothy, don't worry. -1 symbolizes the end of the, like it's just empty linked list. Okay, so let's go back to this example. So now we have, at this point, we're gonna have the best answer. So let's say we're gonna start from the end. This is gonna return 3 right here. And now sub result is gonna be 3 in this call right here. So at the call of this node 2, where sub result is gonna be equal to 3 since it goes to head next. And head next, we're gonna be at 3. 3's head next is gonna be null. So, okay, so we went at 1 and 2. Let me just account for this. Because the way this is going to work out, the sub result part is just going to go deep into the linked list all the way into the end. So that's why I'm going to, increment this right now. So we would have incremented all of these. So I can just, rewrite this right here. This would have been 1. This would have been 2. This would have been 1. So we get to the end, and that's where we're going to be back at call right here, this call right here. And then now here's where we're going to do our comparisons. We're going to want to compare. Okay, let's compare the frequency of 3 with the frequency of 2. And the whole goal of this problem, if you guys remember, you want to get the minimum of the maximum frequencies. So the maximum frequencies in this case would be 2, right? So 2 would be the maximum frequency, not because it's the value 2, but because it has a frequency of 2. So which one has a bigger frequency? In this case, 2 has a bigger frequency. Therefore, we would want to go with 2 since it beats the frequency of 3 in this case, right? And let's say for a different node, it beats out 2. Then in that case, we would want to return that value itself. So if 3 beats out 2, it has a bigger frequency, then you would return 3. But in this case, since it's the opposite is true, the frequency of 2 is greater than 3, then you would want to end up going with 3 for the decision at that node. So we would have an if frequency of subresult is greater than frequencies of head data. Head data is where we currently are, so that would be 2, and subresult right now would be 3. Then we want to go with the one with the greater frequency. So that would be return subresult. So does everyone agree with that? Does return 0 not work for that, or would that cause problems? It wouldn't cause problems since I said only positive integers. Then 0 is not like positive, it's not a positive integer, but I just chose -1. You could have chosen 0. You could have chosen any number that's not positive. And yeah, there are other cases. So that's good that you mentioned that. So the other case would be, the flip side. So else if frequencies of subresult is less than frequencies. So if head data, like the node at head data, so in this case, this would be the case for where we are right now. Head data, which is 2. So let's say f is frequencies. F of 2 beats out f of 3. So in that case, since 2 has a greater frequency, we want to end up returning 2 to this call right here. So yeah, that's what would happen if like what I wrote above was not the case. So frequencies of head data, if that beats out frequencies of subresult, that's where you would want to return head data. And now what's the only other case that I haven't handled? So we handled if subresult is greater, if subresult is less than head data. In those two cases, we just want to take whatever's greater. So we would just return like whichever one gives us the greater answer. Now we have the case where what if they're equal? So if we had a case where it's like the same case, 3, 4, 2, 1, they all have the same frequency, but we want to return the minimum out of all of them. So the way we would do that would be else, and then here you would just check which one is bigger than which one. So right now they have the same frequencies, but we want to return the smallest one out of all of them. So it would be return subresult is greater than head data. And I'm going to do some ternary. I know some people don't like that, but it looks nice. So subresult is greater than head data. So that means that the smaller element would be head data. So if subresult is greater, then we want to return the smaller one. Else, if it's equal or less than, we just want to return subresult. And that would end up giving us our answer. So if we just trace this out, and let me just make sure nobody has any questions on that. Could you explain the if statement returning head data? Sure. So same case. Three, two, two, one. This is the frequency array. So from here, we would have returned 3. So we have 3 and 2, right? So our head data right now, like if we would have recursed all this way down, we would have returned from 3. We would have been currently at 2, and we compared frequencies of 2 and 3. So frequency of 2, f of 2 is 2, f of 3 is 1. But we know that 2 right now is our head data. This is our head data right here. If head is right here at this node. So in that case, you would want to return the node that has, or not the node, the value that gives you the biggest frequency. Because remember, the whole idea is to get the, out of the values with maximum frequency, you want to return the smallest one. In this case, there's only one with a, maximum frequency, but let's do a little edge case real quick, or a different case. Let's add a 1 here, right? So this wouldn't really change much. It would just increment this by 1 since we have another 1. So we know that 2 beat out 3. Since 2 appears twice, 3 appears once. So from here, we would end up returning 2. From here, we're at this node again, this recursive call for this node. Now we're going to see 2 and 2. What do you guys think is going to happen in this case? Does 2 beat out 2? Well, since it's the same number, the frequency of 2 and the frequency of 2 are equal. So it would just be, equal. And since they're equal, that's when we would want to do this check right here. Return subresult is greater than head data. If that's true, return head data, else subresult. In that case, it's the same value. So it doesn't matter which of the two. It would just be subresult, which is also 2. So from this node, you would end up returning 2. Now you're going to compare. What's the frequency of 1 with the frequency of 2? And we notice right here, frequency of 1 has 2, is 2, and then the frequency of 2 is also 2. In that case, the frequencies are the same, but we want to return the smallest of the maximum frequencies. So the smaller of the two, which one is greater, 1 or 2? Since they have the same frequency, would be, in this case right here, we don't return the smaller of the two, which that would be 1. So we would end up returning 1 to this call right here. And now we're just going to compare the frequency of 1 with the frequency of 1. They have the same frequency. And our check would just be if 1 is less than 1, return 1, else 1. So it doesn't matter. We're just going to return 1. And 1 would be the minimum of the maximums. So notice how the ones with the maximum frequencies were 1 and 2. So we have 1 and 2. And then we return the minimum of 1 and 2, which would be 1. And that's how you derive the answer. So does anyone have any questions? Yeah, they'll occur every Wednesday, and it'll be from 5 to 6:45. And yeah, I realized that on DMA and linked lists, I spent a little too much time, especially on some of the easier cases. So next time I can go on for a little longer and finish up because the session was meant to be on DMA, linked list, stack, and queue, but we pretty much only got through DMA and linked list. And 6:45 is almost here. So I'll stretch it out a little longer next time, and we can do stacks and queues. And this was my first session. I didn't know, I'm not too great with timing and all that. So, but now I know what I have to do and how to time myself and everything. So definitely I'm gonna go into stacks and queues on the next session, and then I'll also dip into binary trees as well. So yeah, I think that's a better way to focus on it because linked lists are kind of like foundation for certain variations of stacks and queues. So I guess it's good that I put some more time into linked lists. And also, yeah, this dealt with recursion, frequency array, and linked list. So we kind of hit three topics in one. But yeah, it's gonna be every Wednesday up until the foundation exam, and yeah, so it's gonna be. I think the last Wednesday is gonna be the week before the foundation exam. Foundation exam is on the 21st on a Saturday, so that'll be on the 20, on the 18th would be the last one. Yeah. No problem, no problem. Yeah. Is it everyone's first time? I see that. Oh, Nico has it's his second try. Okay, cool. Second as well. Okay. Yeah, it's no problem. I'll help you guys out. Help you guys out. I'm gonna see if I can get a room for. Well, actually, I'm not gonna see. I'm gonna ask Eli, which is he's the vice president, I believe, of Night Hacks, and see if I can get a room. So maybe I can help people out in person because I know it's a little harder over Zoom, to deal with people's questions and explain stuff. But you know, oh, yeah, you do remember. Okay, that's cool. Was that for Guha? Okay, cool. That's awesome. So does anyone have any questions or any like critiques or anything? Because yeah, it was my first time, so feel free to say anything. Like, did I do bad? Should I have distributed my time better? Anything helps. Check chat more. Oh yeah, I just downloaded Zoom for to do this. So I think I turned notifications off. So that's why like I only saw chat if I looked at it. So yeah, I'll turn notifications on. But yeah, do you guys have any topics that you want to see next time? Like aside from stacks and queues, like is there anything that anyone is specifically bad on or you have difficulty with? Pointers and dealing with parentheses. Oh, actually, I remember I said at the very end, was it you, Timothy, that asked me about the pointer arithmetic? Okay, yeah. Yeah, and I'll definitely do foundation exam question. The thing is, I just don't know where everyone's at. So that's why I tried to like go from the very basics, but I think to some degree, like I went a little too basic, so anytime we can do recursive coding would be nice. Yeah, that's why I made this problem because I knew it would be like if you guys notice, you have to recurse like kind of post order, go all the way to the very end before you have your answer. And on the way back from the recursion is when you calculate and do all the logic of the program. So, recursive from that was a pretty good one. Yeah, I know. Yeah, it was definitely harder to come up with when you don't have time for it. But since I'm on a time constraint, I kind of had to go through it a little quick. And yeah, Timothy, I'll go through that real quick. I'll go through that real quick. Like we have a couple minutes, or it's already 6:44, but I'll just do it real quick. So, pointer math. I remember, let's say you have an array. Funny enough, people in my CS1 class, they used to always make fun of me because I used to do stuff with pointers like that. Like I used to do all types of crazy stuff with pointers. So if you're doing pointer math, it works very similar to how an array indexing would work. So, what we're used to, I'm gonna use X, I'm sorry, but I'm gonna use X. X is less than 5. We have an array of size 5, X plus plus. Say you want to print, it would be pretty much same type of logic. Array of X. So this would print out 1, 2, 3, 4, 5. But if we think about what this is right here, this is pretty much the same thing. Like whenever you call an array name or use an array name, it's pretty much equivalent to a pointer to the start of the array. And the start of the array is really just array of 0 with the address of that. So this is pretty much whenever you pass something in as a a function, even if it was statically allocated like this array 5, like so we have f, a function f, and then we pass in array. Array can actually be a pointer because if you think about it, let's say just int n, which would be 5, but array pointer, whenever you do this, you're getting the address. Remember, addresses are represented, you point to them in C with pointers. So pointer math, it works very similar, where whenever you do something like array of 0, what's really going on is you're doing an array plus 0 and array of 0 plus, actually in this case you wouldn't be doing plus, but this is pretty much what goes on, and then you just dereference this pointer.
Hello?
Hello?
Yeah, can you hear me clearly? Or is it
Yeah, I
noise?
can hear you.
Like, yeah, what I was gonna say was like, my understanding of it is like, anytime you see like a pointer plus something, it's like one of my friends told me just think about it, whatever the number is, multiply it by the size of bytes that the data type that the pointer is. If
Yeah.
that makes sense. Is that the case? Because like I'll see like not questions, but like I'll see situations where it's like the pointer is within a parenthesis and then there's a dereference, or the dereference is like inside like
Okay,
that.
okay.
That's what's
I see your
confusing me.
question.
It's like
So, okay,
like
so
where does the
so
dereference
you're
start
not
and
saying like
end?
moving through an array with integer or with pointer arithmetic, right? You're not saying like moving through an array, or are you saying just like accessing stuff with pointers and like how incrementing and all that stuff works depending on
Yeah,
how you order it?
yeah. How do I read that? Like how like because I have
Oh, I got you. I got you. Okay,
yeah,
okay.
because like some
So,
questions would be like parenthesis, open parenthesis, dereference sign, the pointer, close parentheses, and then the increment. And that's so completely different than say the increment and then dereference and then pointer. So it's like I have
okay.
issues reading that.
Can you repeat the first example so I can write it
So
down?
let me see if crap, it's computers. Let me see if I can type it in. So it'd be pointer. So it'd be something like this is completely different
You said
from
it on
something.
Zoom?
Yeah. Something like that,
Okay.
from my understanding, is completely different from something like this right here. And it's like there's several other versions of that, but like they mean
Hmm.
different stuff, and that's like it confuses me.
Okay, I see. So you said star p plus plus, and then you have plus plus star p. Okay, so in a way, they're actually kind of similar, but not really. So let's say p points to, let's say we have arrays. So you see this array up here?
Mm-hmm.
This array up here. So let's say we point integer star p equals, and let's say array of 0. So this is pointing to this element right here,
Okay.
right? Okay, so it's pointing to that element right there. And now what I'm going to do is I'm going to go through this code right here. So what it's doing, it's dereferencing the pointer. And if you think about like just order of operations in like math, for example, what happens in the parentheses goes first. So it's like, PEMDAS, right?
Got you.
So what happens in the parentheses is going to go first, unless it's something like this right here. It's going to read it left to right, but in this case, what's going to happen, since you're incrementing afterwards, it's going to do star of P, and P is pointing to the first element of array. And at that address in memory, like let's say this is memory right here, it's going to be storing a 1. So what it's going to do, it's going to dereference, and now it's going to say, okay, I have a 1 right now. So the value of this right here, if you print it, it would be 1. But if you end up doing plus plus, it's going to take that address in memory and increment it by 1. So now this is actually going to be 2. So this is pretty much equivalent to when you do like array of 0 plus plus. That's actually what it's doing.
Okay.
So it takes the address of array of 0, it dereferences it, and then so I know that looks kind of crazy, but what it does, it takes the address right here, it dereferences it to get like the value inside of it, and then from there it increments the value inside there. So now when you go look at it later, it's going to be 2 instead of 1. And meanwhile, on the other example that you gave me, if it was plus plus star P, let me just erase this stuff right here. So if you do plus plus star P, so we're gonna have star of P. Oh, and I can see why this one's gonna be a little weird. Yeah, star P plus plus. Huh.
Well, I guess I also want to ask, realistically, do you think I'll probably see this on the exam?
No. I'm not
Okay.
gonna lie. Like I'm looking at this one, it's kind of weird because you
Yeah.
have to know for these type of things. You have to know like the order of operations and like what
Yeah.
comes first, what executes first, and all that stuff. And typically, this is something you can see like for sure you can see something like that.
Okay.
But I would seriously doubt they're gonna do something like this because this goes into it's like a whole different level. But they might do something like this where it's easier to tell because the parentheses order of operation is going to go first. But something like this, I seriously doubt they're going to give it to you.
So with the parentheses
Like,
around it.
yeah, with the parentheses around it, it would dereference first and then it would increment.
Okay, so the
So
same thing as the one on the left.
yeah, pretty much. But let's say you were gonna set it to a variable. This is where it's gonna change a little bit. So if you're gonna do like int a equals star of P plus plus, and then you do int B equals plus plus star of P. So in this case, let's just go back to this example right here. So this is still pointing to the first value in the array right here, right?
Yeah.
So it's pointing to this right here. And then if we go to A, then A is going to dereference that. This is going to turn into 1. Like it's going to index into array of 0 because that's what it's pointing to. And then it's going to do plus plus. So now it's going to set A is going to be equal to, it's going to be 2. But what A is going to assume is this part right here. A is going to be equal to 1. But afterwards, after you set it equal to 1, you're incrementing 1. So then the next time you use it, when we get to B, like after this line right here, this is actually going to be 2. Like this is going to be 2. So A is going to assume the value of 1 because in order of operations, we did this part first. But in this, like when we get to this line, like right now, it's going to be equal to 2, if that makes sense. Because we just passed
you
that line.
changed the pointer.
Yeah, exactly. Because we dereference and then we increment. So now right here it's going to be 2. But now B is not going to be equal to 2. B is actually going to be equal to 3 because right here it's going to dereference it again, but it's going to increment it before, like it's pretty much going to do star P plus 1. That's pretty much what's going on. So then it's actually going to be the value of b is going to be 3. But meanwhile, if we were to do something else like this, like we were to put this on the other side, the
Mhm.
value of b would actually be 2, but after this line, then it would be 3. Because
Mm,
it does the same thing here. It would still do array of 0, then increment, and then it would be 3 after this line. But at this line right here, it would take the value of 2,
okay.
if that makes sense.
That makes sense. That makes sense. Okay.
Yeah, it's just like if it happens before, b is
Mhm.
going to take the value of what you incremented to. But if it happens after, it's going to take the value before incrementing. But after that line, it's going to be incremented.
Okay.
Yeah,
Okay.
yeah, yeah.
That makes. I just didn't want to spend as much time on something that's most likely not going to be on the
Yeah,
exam.
yeah. To be honest, they're probably they might give you a little tracing on something like that, but
Yeah.
something like what you showed me, like, yeah, probably not. Like I
And
seriously doubt
I guess something else from the previous exam, I remember there was something, a question where it's like it was dealing with character pointers and like a buffer point and something like it doesn't have to be now because we're way past the thing, but like if at some
it.
point
Yeah,
during these sessions, if you could touch on that.
I got you. Okay. Okay, cool. Yeah, yeah. I'll if you could send it in the Discord, like the foundation exam for night hacks,
Yeah,
and then I'll take a look at it. But
bet.
yeah, as for this one though, I'm gonna cut it off here. But yeah, next time is gonna be stacks, Q, and also I'm gonna go more into foundation exam question.
Okay. Hey man, I appreciate this session, man. It really helps.
Really? Okay, okay. What part do you think helped the most?
Um, Definitely the question. That's why I feel like Nico was probably asking for the questions because it's like you're explaining it, and then once you hit the question, it's kind of like, oh yeah, she had to think. You're like, oh man,
Yeah, yeah.
you
I
gotta apply
kind of threw it
yourself.
out of nowhere. Yeah.
Yes,
Okay,
I'd say
okay.
that really like helped a lot.
Yeah, yeah. No problem. No problem. All right then, guys. I'm gonna cut it off here, but it was good. It was good hosting and good talking to you. All right. See you guys.